Hello and good day everyone. We are Group 3 who will be presenting to you the Universal Oil Products or UOP Sulfolane patented process. To start off, I would like to first introduce my team who made this presentation possible. Razon Gerald, who made the intro and overview, Malinis Patrick, who made the details and equipment, and yours truly, Dayap, who made the flow and presented to you the PowerPoint in front today. To start off, we need to understand what is the sulfolane process. Well, it is a trademark of Honeywell International Incorporated under their Universal Oils product or UOP, designed to recover benzene and toluene at high purities with a 99.9% weight ASTM refined benzene 545, toluene with less than 1,000 weight parts per million of non-aromatics, at least 99.5% recovery rate of benzene and toluene, designed to have a maximum energy efficiency while having low solvent consumption. Since 1965, UOP owns the license for this process. Since then, it has been improving based on the developed features and techniques by the company Honeywell. Uses the solvent tetrahydrothiophene 1,1-dioxide, which is also known as sulfolane. Can either use both liquid-liquid extraction LLE and extractive distillation or ED in its system, which is traditional, or just ED alone based on the feed provided. But what are the ideal solvent properties for the process? Since the process needs to have a solvent for it to work, what is its ideal solvent to be used? Well, the considerations for the solvent to be used in this process are as follows. It revolves around the relationship between the solubility and the selectivity of the solvent. Solubility is the capacity to absorb aromatics, and selectivity is to differentiate aromatics from non-aromatics. Studies reveal that for hydrocarbons with the same number of carbon atoms, solubility decreases as follows: aromatics to naphthenes to olefins and then to paraffins. For hydrocarbons in the same homologous series, solubility is inversely proportional to the molecular weight, and the selectivity is inversely proportional to the hydrocarbon content of the solvent phase. But out of all the solvents in the world, the sulfolane process uses the solvent sulfolane for it to be used, hence why it's called the sulfolane process in the first place. But why is it that the sulfolane is the best solvent for this process? Well, that's because above all solvents, sulfolane exhibits better aromatic solubility and selectivity compared to other commercial solvents. This results in a lower solvent circulation rate and lower energy consumption for the sulfolane process design. In addition to these, sulfolane has three physical properties that makes it best the solvent to be used in the process. That first property is high specific gravity of 1.26. This makes way for the process to utilize the aromatic capacity of the solvent effectively while still having a large density difference between the hydrocarbon and the solvent phases. This gives way for a lower requirement for the extractor diameter and equipment size. Another notable property of sulfolane is its low specific heat of 0.4 calories per gram per Celsius. This reduces the heat loads in the fractionators. This also minimizes the duty on the solvent heat exchangers. And lastly, high boiling point at 287 degrees Celsius. This facilitates proper separation of the solvent from the aromatic extract during the process. So, in summary, the reason why sulfolane is the best solvent for the sulfolane process, hence its namesake, is because of three things. One, it is very economical. It helps lessens the utility cost and energy cost. Two, it is very soluble in aromatics. And three, it is very selective that it knows how to differentiate the aromatics from the non-aromatics. The next question on your mind is, why do we need to discuss the sulfolane process in the first place? It's because of the integrated UOP Aromatics Complex. This complex is the different set of combined chemical processes that helps convert naphthalene, which is a crude oil obtained from the chemical or the petroleum industry, and convert it into different types of petrochemicals such as benzene, toluene, and different other hydrocarbons. And the sulfolane unit is one of these chemical processes integrated in the UOP Aromatics Complex. The sulfolane unit is part of the integrated UOP Aromatics Complex, and it is connected to the reformate splitter column such that the C6-C7 fraction hydrocarbons from the overhead product of the splitter serves as a sulfolane process feed. After the sulfolane process, the aromatic extract reduced is to be clay treated to get rid of olefin traces and for the benzene and toluene to be recovered using simple fractionation. The raffinate from the process is used for other purposes such as being mixed into gasoline pool or aliphatic solvents. So where is this sulfolane unit located in this UOP Integrated Aromatics Complex in the first place? Well, as you can see, it's right here. This is where the sulfolane unit, or our very own process of discussion, takes place. And as you can see here, we can identify the feed to the sulfolane unit comes from the reformate splitter, and we have two outputs of the sulfolane unit. One is the raffinate, and the other goes to the benzene column. So what are the feed and the products of the sulfolane unit? And we'll discuss them in the following slides. We also need to know what are the different possible applications of this sulfolane process. Well, it can be used as a benzene reduction application, where it can reduce benzene concentrations in a gasoline pool. Useful for meeting a certain gasoline requirement. In a benzene reduction application, some of the reformate input bypasses the sulfolane process and mixes back as part of the gasoline pool, which is depending on the required benzene concentration reduction. The benzene product extracted can be sold in the petrochemical market as it is high in purity. So in order to understand the sulfolane process, we must first understand what is its basic concept or theory. So the sulfolane process follows this simple diagram, and it may look intimidating at first, but it's just telling a story from how the feed turns into the final product. The feed, which is not yet named, is aimed to be turned into one, the raffinate, which this raffinate contains low aromatics and high non-aromatics. So a low concentration of aromatics and a high concentration of non-aromatic compounds. And another product from the feed is an aromatics extract and solvent. So this product is high in aromatic compounds and high in solvent concentration. So how do we convert the feed into two different products? Well, the feed must first then be forwarded into a main extractor that flows upward. In order to extract the aromatics from the feed, we must then pursue a lean solvent also being fed to the main extractor, but instead of flowing upward, it flows downward, creating a counter current exchange. The main product of the main extractor is, of course, the low aromatics and high non-aromatics raffinate, and the output or the bottoms of the main extractor is a high aromatics and low non-aromatic solvent, the exact opposite. This bottoms is then forwarded into a backwash extractor, which is letting it flow downward, while also having a light non-aromatic hydrocarbons flowing outward, creating another countercurrent exchange. The raffinate is then fully heavy non-aromatics, which is then fed back to the main extractor, also fed countercurrently, so that it will increase the efficiency of low aromatics and high non-aromatics raffinate. The bottoms of the backwash extractor is high aromatics and low light non-aromatic solvent. So in the backwash extractor, they separate the heavy ones from the light ones. The heavy going up and the lights going down. Quite contradicting, but it's the backwash extractor. Then, this feed is then forwarded into an extractive stripper where it is flowing to different sides. Its two products in the extractive stripper is one, light non-aromatic hydrocarbons, which is then recycled back into the backwash extractor, and the other, the bottoms, is the final product, the aromatics extract and solvent. So all in all, the basic concept is there are three main units: the main extractor, backwash extractor, and extractive stripper, and ideally every flow must be in a counter current exchange. So we understood the basic concept of the sulfolane process, but how does it work in actuality or in an industrial sense? Well, it follows this certain industrial diagram, and it's way more intimidating than the first one, but again, we'll just have to discuss it one by one on a story on how it turns from a feed into the final aimed product. Remember that the feed, which is also still not named, aims to be two of the final products: one pure aromatics extract and one raffinate product. So how do we get from here to there? Well, the feed is forwarded into a feed surge drum and then forwarded into an extractor. It follows the concept. So as it enters the extractor, every unit, remember, every unit still operates counter-currently. As it enters the extractor, lean solvent also enters the extractor. The raffinates is low aromatics in content, and the bottoms is high aromatics in content plus the lean solvent. So, where does this lean solvent bottoms go? Well, it go forward into a stripper so that it would separate the non-aromatics from the aromatics and the solvent. Then the non-aromatics is in vapor form. It must be forwarded into a condenser to turn back into a liquid form and refed back or recycled back into the extractor to improve efficiency and collection. So, where does the bottoms or the aromatics and solvent go? It goes to the recovery column, where it is also being fed stripping steam that will remove the aromatics from the solvent, thereby having a pure aromatics extract, and the bottoms is just pure solvent with very minimal aromatics left behind. And this solvent is hot due to the stripping steam, which steam by nature is also hot. The hot solvent is then split into two sides or two lines. But before we discuss where does the hot solvent go, we must first go back to the low aromatics raffinate, where in the raffinate it is a vapor form. Then we first condense it to turn back into a liquid form, and this liquid form is then forwarded into a wash column. This wash column is also being fed water, so that one of the products is the raffinate product, which is our aim product, and the bottoms is stripping steam. And this stripping steam is also being split into two parts. The first part is being fed, the stripping steam is being fed into a solvent regenerator with the hot solvent so that it would yield a product of regenerated solvent, and this regenerated solvent, which is the green line, is recycled back into the recovery column to improve efficiency and collection of the pure aromatics extract. But the stripping steam is hot, and the stripping steam from the wash column is cold since it's cold water, and the hot solvent is hot due to stripping steam. Then it's just a simple heat exchanging unit to transfer all the heat from the cold steam into the hot solvent so that the solvent will be cool, and it will be recycled back into the extractor, hence connecting back into the lean solvent feed stream of the extractor itself, thereby further increasing the overall efficiency and collection of both the products, raffinate product and the pure aromatics extract product. Now, we need to discuss what will happen to the products itself. What will happen to the raffinate product? Well, the amount of sulfalane solvent retained in the raffinate is negligible, and the raffinate product is commonly used for gasoline blending or aliphatic solvent applications. And our other product, the pure aromatics extract, is the one that we want. The extract product from a sulfolane unit may contain trace amounts of olefins and other impurities that would adversely affect the acid wash color tests of the final benzene and toluene products. To eliminate these trace impurities, the extract is clay treated prior to fractionation, and the treated extract is directed to the aromatics fractionation section, where high purity benzene, toluene, and sometimes mixed xylenes are recovered. The toluene product is often recycled to a UOP unit for conversion into benzenes and xylenes. Mixed xylenes may be routed directly to the xylene recovery section of the plant for separation into paraxylene, orthoxylene, and metaxylene products. So in short, the feed into a sulfolane unit is aromatics but has also impurities, and the sulfolane unit separates the impurities from the pure aromatics extract, and this pure aromatics extract is then forwarded into other units so that it will help separate truly from the xylenes, from the benzenes, and toluenes, so on and so forth. Now we get to the part where what is the feed, or what is being fed to the sulfolate unit in the first place? Well, it can be a benzene toluene cut from a naphtha reforming unit, a pygas byproduct from an ethylene plant, or it can be a coke oven light oil for aromatics recovery. And to handle the said feed or feedstock, before being sent into a sulfolane unit, the reformate must first be stripped in a debutanizer column to remove the light ends. In the case of a pygas and coke oven light oils feed, hydrotreating must be done first to remove dienes, olefins, sulfur, and nitrogen. The different specifications of feedstock is summarized in Table 2.2.1 in Mayer's Handbook of Petrochemical Industries, where the total sulfur contaminant has an effect, it contaminates the product and limits the total sulfur of 0.2 parts per million maximum. Same with thiopene and total chloride. For bromine number, the effect of this contaminant causes higher solvent circulation and increased utility consumption, and the limit for the bromine must be a 2 ppm max. For the diene index, its effect causes higher solvent circulation and increased utility consumption, and its limit in the feed must be 1 ppm. And the dissolved oxygen, its effect could cause degradation of the solvent, and we must limit the contaminant to 1 ppm maximum. So in short, this table summarizes the possible feed components, and these are considered as contaminants. And of course, these are the different effects the contaminants could have in the overall process, and we do not want that, for it could cost us money, time, and effort. Hence, these are the guidelines for maximizing or the maximum amount of contaminants the feed could handle. If it goes way past the maximum amount, we must try to further replenish or purify the feed even more to prepare for the unit to prevent any further damage that could cause money and power or manpower. Given that, how well does the sulfolane process perform? Well, the performance of the UOP sulfolane process has already been well established in more than 100 operating units. It also demonstrates the lowest energy consumption of any commercial aromatics extraction technology. The efficiency of benzene, toluene, and aromatics recovery of sulfolane are as follows. Benzene recovery exceeds 99.9% by weight. Toluene recovery is typically at 99.8% by weight. And typical recovery of xylenes exceeds 98% weight, and a recovery of 99% by weight has been demonstrated commercially with rich feedstocks. So its process is actually very good. It's less in the economics and more on the product and the objective of the overall process, which is trying to find or purify or to isolate a mixture of benzene, toluene, and xylenes, removing the impurities from the feed to prepare it for the fractionation. Important notes on sulfolane process performance is that the UOP or UOP sulfolane units routinely produces a benzene product with a solidification point of 5.5 degrees Celsius or better. The toluene and C8 aromatics obtained via sulfolane process are of extremely high purity and easily exceeds nitration grade specifications, but this depends more on the design operation than the extraction efficiency of the sulfolane unit itself. The purity and recovery performance of an aromatics extraction unit is largely a function of energy consumption. As stated, sulfolane unit consumes the lowest energy compared to other aromatics extraction energy, which requires 275 to 300 kilocalories of energy per kilogram of extract produced, even when operating at the maximum possible recovery. Expected solution losses of sulfolane solvent are less than 5 parts per million of the fresh feed rate to the unit. When discussing the process, we talked about extractors, strippers, so on and so forth. But specifically, what are the different equipments used in the sulfolane process? Well, in the conventional unit, so there are two types of units, conventional unit and the extractive distillation unit. They are still the same sulfolane process, but different configuration. This is the conventional unit or conventional configuration, and one of the equipments used in the conventional unit is an extractor. An extractor that uses rain deck trays to contact the upward flowing feed to the downward flowing solvent. Another equipment is the raffinate wash column to recover the residual solvent carried over in the raffinate from the extractor. Another one is a stripper column to remove any light non-aromatic hydrocarbons in the rich solvent by extractive distillation. Another one is a recovery column to separate the aromatic extract from the sulfolane solvent via vacuum distillation. And another one is a solvent regenerator. This machine is also utilized in the conventional unit, and it is a short vertical drum used to remove polymers and salts formed because of the degradation of solvent by oxygen. The regenerator is operated under vacuum and runs continuously. So you might wonder, in my explanation of the process, why is there no solvent regenerator? Well, to further simplify the process in an easy to digest manner, I omitted the solvent regenerator, but most probably there's always a solvent regenerator in every conventional sulfolane process unit. As such, you can see in the original diagram of the raw integrated parts of the sulfolane, where in the sulfolane industrial process diagram, there is a solvent regenerator added. Another one is a sulfolane process heat exchanger. So this heat exchanger, there's approximately 11 heat exchangers in the actual sulfolane process design process flow diagram, and these are typically designed in a typical unit, and it is highly heat integrated, meaning it is very highly used due to the numerous cold and hot streams indicated in the sulfolane process unit. Since we also covered the conventional unit, we also need to discuss the extractive distillation unit. So this unit requires less equipment compared to its conventional unit configuration or counterpart, and the following equipments can be eliminated when discussing the extractive distillation. The rain deck extractor and raffinate wash column can be negligible in the extractive distillation unit. Also, the solvent in the raffinate is eliminated by the extraction distillation in the column reflux. In the case of benzene-only feed, all the equipment associated with water circulation and stripping steam can be eliminated. So, what are the different specifications the equipment use? So, what are the different heuristics or design properties that designers or chemical engineers use when dealing with sulfolane process flow diagrams? Well, in the extractor, the major heuristics in extraction or for the extractor in the sulfolane process unit is that the rain deck trays act as distributors by dispersing droplets, hence the term rain, of solvent moving down through the extractor to facilitate the dissolution of the aromatics components into the solvent phase. And a typical solvent extractor column contains 94 rain deck trays. Another heuristic for the raffinate wash column is that the raffinate wash column uses jet deck trays to provide counter-current flow between the wash water and raffinate. A typical wash column contains 8 jet deck trays. A stripper column heuristic is that a stripper column for sulfolane unit contains 34 sieve trays, and the recovery column uses 34 valve trays. And are there more considerations to take note of when in terms of equipment design? Well, there are. Well, a sulfolane unit is approximately 80% of the cost of a liquid-liquid extraction or extractive distillation unit. All the equipment for the sulfolane unit except the solvent generator are made of carbon steel. So the material of construction for each of the equipment must be of carbon steel manufacturing design. The solvent regenerator reboiler is constructed of stainless steel. So every equipment is constructed using carbon steel except for the regenerator, which is constructed using stainless steel. Maybe the reason is to avoid any possible corrosion effect that it may have, that it may possibly have due to it being a solvent acquirer or handler. Noting the equipment, noting the process, noting the theory, we must all ask ourselves the very realistic question, how much money are we talking about here? So given if you're an investor trying to further increase or improve this process design, or you are the designer itself who wants to design something similar to the sulfolane process unit, how much money are we dealing with here? So, in terms of investment and utilities, table 2.2.2 summarizes that certain information. In terms of construction, it costs 13.5 million US dollars, quite a hefty sum. But in terms of utility, electricity costs 390 kilowatts, uses 390 kilowatts. High pressure steam is 27.5 metric tons per hour. And for cooling water, it's 274 cubic meters per hour. Again, quite a hefty sum of resources and money. The basis of these utility investments and in cost and consumptions is a basis of 25 metric tons per hour of toluene product, 11.8 metric tons per hour of benzene product, and 54.5 metric tons per hour of benzene toluene reformate feedstock. But with all said and done, knowing the money, the equipment, the process, does it have actually any experience in commercial settings? Well, we discussed earlier that there is actually 100 working operating UOP units at present. But in terms of history, does it actually work? Was it a smooth history flow? Well, as surprising as it is actually a smooth history of a commercial timeline. In the 1950s, UOP has licensed 4 different aromatic extraction technologies, including the UDEX, Tetra, Carop, and the main player, sulfolane process. UOP's experience in aromatics extraction encompasses more than 200 units ranging from 2 to 260 metric tons per hour of feedstock. In 1952, UOP introduced the first large-scale aromatics extraction technology, the UDEX process, which was jointly developed by UOP and Dow Chemical. 1950 to 1965, UOP licensed a total of 82 UDEX units. In 1962, Shell commercialized the first sulfolane units at its refineries in England and Italy. In 1965, the success of Shell's units resulted to an agreement making UOP an exclusive licensor of the Shell sulfolane process. In 1968, researchers at the Union Carbide discovered that tetraethylene glycol had a higher capacity for aromatics than the solvents being used in existing UDEX units. Union Carbide then began offering this improved solvent as the Tetra process. In 1986, Union Carbide commercialized the Caron process, a process similar to UDEX and Tetra processes, but takes advantage of unique two-component solvent system that nearly equals the performance of the sulfolane solvent. 1988, UOP merged with the CAPS division of Union Carbide, resulting to the UOP offering both the sulfolane and Caron processes for aromatics extraction while continuing to support the older UDEX and Tetra technologies. So the history of sulfolane process is very hefty and many. It's in terms of improvement, for it comes with its brothers and sisters of processes, the Tetrax and the UDEX, and even now it's still considered a very important process in the petrochemical industry today, such that it's being kept on improving, not only in the terms of sulfate itself, but also its other processes that also is being connected with the sulfate unit, such as the UDEX and Tetra units. In 1995, UOP had licensed a total of 120 sulfolane units throughout the world, and in 2002, the 21st century, UOP had licensed a total of 7 Caron units. 6 of these units are conversions of UDEX or Tetra units, and 1 is a new unit. So it goes to show that the sulfolane unit is really an important petrochemical unit in the petrochemical industry today, as it's still being used by different chemical processes, all for the aim of obtaining that benzene and toluene purity mixture. And these are our main references. So it's actually just 2 references. One of our main reference is the Handbook of Petroleum Refining Processes, 3rd edition by Robert A. Mayers, and our sub-reference is from the Honeywell website itself, Honeywell UOP from Aromatics Recovery. And again, I am Ron Dayap, representative of Group 3, and I thank you all for listening to our presentation concerning the UOP or the Universal Oil Products Sulfolane patented process. Thank you and good day.